So, in the last lecture I have discussed about the seismic reflection test. So, and this is the seismic reflection survey or test, where the velocity of the soil layer is determined and the thickness of the soil layer is determined. And as I mentioned that this test where we have to identify the travel time of two waves. One is the direct wave from the source to the receiver, another is the reflected wave. So, this is the reflected waves. So, that is why identification of these two waves is sometimes difficult. So, then we will go for the next test, which is seismic refraction test. Another one, here we are measuring the velocity of the soil layer, layer 1, and the thickness of the layer 1. So, this method is suitable if the soil is the homogeneous kind of soil, but if the soil is a layer kind of soil, which is the common in most of the cases, then you have to go for the next technique, which is seismic refraction survey. Now, as I already discussed, here we will apply the hammer blow. So, and these are the receivers. So, these will receive the wave, and then it will identify the travel time of the wave from the source to the receiver, either it is direct or the reflected. And we can generate different wave depending upon how we are applying the hammer blow, either it is P wave or the S wave. Now, these are the two curves that I have discussed, and instead of going one particular two curves, we can go for the single curve making a square, x n square and t r square, and with that square curve we will get a straight line, and from the straight line we can get the V p 1 and the z value, and these are the expression. So, next one that we will go for the seismic refraction survey. Now, in the seismic refraction survey, so this is the source, and you have to again put the n number of geophones, and here we have, say, this is the soil layer, it is also maybe the soil layer. So, or the bedrock, that initial it is the bedrock, because it is the seismic reflection we got a it is homogeneous case, but here it may not be the homogeneous, it can be different layer soil also. So, here instead of bedrock we can go for a soil layer of different thicknesses, different soil layers with different thicknesses. So, what will happen here also, we put the hammer blow and the receiver. So, instead of measuring two waves, here we will the receiver will measure the travel time of the first wave, the wave that will reach the receiver first. So, that we will call it the first arrival time of the wave. So, that can be the direct wave, that can be the refracted wave, that can be the reflected wave, because when you are talking about refraction survey, there is a possibility there can be a reflected waves also. There is a possibility there can be a refracted wave, this can be a direct wave. So, the receiver will indicate, so the first arrival time of the wave. So, that is the advantage. Here we are not measuring two different waves, whether one is direct, one is reflected. Here we are measuring the first wave arrival time. It can be direct or reflected or refracted. So, now, so this is the way we are getting. So, now how we will get the properties of different soil layers. So, here another advantage is that we can determine the thickness of different layers and the velocity of the different layers. So, let us again derive the equations. So, how we will determine the properties here. So, what we will, so suppose this is the ground surface, where this is the source and this is different layer. So, suppose the layer 1, this is V p 1, this is layer 2, V p 2, and this is layer 3, say V p 3. So, now we are putting geophones. So, this is our geophone and this is the source S, and then again if this is the source, there will be n number of waves. So, there will be one wave which will reach this geophone directly. So, another wave, there is a possibility that it will reach by this reflected rays. So, this is the direct, this is the reflected, and now there will be a refraction also, that we did not consider in the previous case. So, how this is the refraction? So, now suppose this is the wave. So, now depending upon this is the wave which is coming here, depending upon the density of the soil, the wave, the refracted wave can move away from the normal or towards the normal, because this wave velocity is the function of density of the soil. Now, it is expected that as the density of the soil increases, the wave velocity will also increase. Okay? And if the density decreases, the wave velocity will also decrease. So, now if we can say that this is the direction of the wave. Okay? So, this is the direction of the wave. Now, if the wave, so suppose if that V p 1 is greater than V p 2, that means this is the high speed material, this is the low speed material. So, the wave will refracted towards the normal. So, that means if V p 1 is equal to V p 2, then this will be the possible, or if I use the different color. So, this will be the possible path of the refracted wave. If this is the case, then this is case 1. So, this is case 1. Now, if this is case 2, that V p 2 is greater than V p 1, then what will happen? This wave will refracted away from the normal. So, in that case, so these, if I take again a different color. So, this will be the travel path of the wave. So, this is I and this is another angle, or sorry, this is the angle alpha, alpha is this angle. So, I can erase this line. And now, so now what does it mean? It means that we have to receive this refracted ray by this receiver. So, this is only possible if these refracted rays follow this blue path, because if it is follow a red path, then it will never reach to the surface. So, where we place the geophone. So, that means we have to follow this blue path. Now, if this has to be followed by this blue path, then that means the one condition is that we have to always follow the case 2, where your velocity of the second layer must be greater than the velocity of the first layer. You have to remember this thing. This is very important, that you will get the good result or the better result if your velocity of the layer increases with depth. That means, if the velocity of the lower layer is greater than the velocity of the upper layer, then only you will get the good results. Otherwise, and this is most of the cases it is common, because we have the velocity of the lower layer is greater than the velocity of the upper layer because of the overburden pressure. So, and because of that we will always get this type of layering, where the density increases with depth. So, the velocity will increase with depth and it will follow this path. So, this is one thing. So, that means, now there will be one particular. So, this is important. Now, if sometimes we do not have this type of layering and we will get not good result, then you have to go for the third option, that is seismic cross hole survey. So, we will discuss this about the seismic cross hole survey. So, now if we are placing geophone. So, there is a particular wave where, because of this angle, instead of this wave following this path, it will follow this path. Okay? So, that means, if I draw it in fresh, so there is a particular. So, this is the geophone, this is the S. So, this is the ray. So, it will follow this path. So, this angle in such case is known as critical angle, when this alpha value is equal to 90 degree. So, if is follow this path, then this angle is called the critical angle. So, IC is critical angle. So, alpha will be equal to 90 degree. So, when it follow this path, again here it will follow this reverse option and it will follow the reverse path like this. So, it will again IC. So, this total things will be completed. So, it will reach into the ground. So, now there is another question, that why we have considered this path, because when this is the point, your refracted ray can go from this point onward, it can go like this also. Suppose this is the path, it can go like this, it can go like this, it can go like this also. But we have considered this path because we have placed geophone here. If you place geophone here, then we have to consider this wave or this path of the refracted rays. So, as we have considered this one, so this is the geophone. So, now here there is the three cases, three rays I have discussed. One is the direct, another is the reflected, another is the refracted. So, definitely direct ray will always reach fast compared to the reflected rays. So, that is okay, because this reflected rays travel path is more than the direct rays travel path, and we are talking about the first arrival time of the wave. And another option, that when this refracted rays is travel with this path, when it is traveling with this layer, it is VP1. When it is traveling here, it is VP2, and this is also VP1. So, you can see when this length of this zone increases, so there is a possibility that this wave may reach fast compared to the direct rays, because our VP2 is greater than the VP1. Now, so that means we are removing reflected ray. It will not reach fast, because either the direct ray will reach fast or the refracted ray will reach fast, because refracted ray this velocity is greater than the VP1. So, we are now removing the reflected rays, because we are talking about the first arrival time of the wave. So, reflected ray will never reach first. So, we are removing this reflected ray in this form here. So, we are now considering direct ray and the refracted ray. So, if we increase the distance from source to the geophone, the possibility of the refracted rays to reach the geophone will increase. So, there is one particular distance where the direct ray and the refracted ray will reach at the same time. So, if you place geophone there, that distance is called the critical distance. So, there is a critical angle similar to critical distance also. Critical distance means where the direct ray and the refracted ray will reach at the same time to the geophone. So, now that angle is called the critical distance. Now, next we are considering, so finally, what we are doing. So, we are considering for the derivation purpose, we are considering this is the geophone, this is S, and we have considered this ray because our geophone is placed here. So, this is VP1 and this is VP2 and this is VP3. Remember that VP3 is greater than VP2 is greater than VP1. So, now we are quickly I will give you the expression of the derivation. So, that means here there is a direct ray. So, similarly I am doing the derivation for the two layer system only. So, this is the first layer and this is the second layer. So, that there is a direct ray T d which is again x n divided by V p 1. So, this is the x n and there is a, so we know that this is if this angle is alpha 1. So, sin alpha 1 divided by V p 1 and this angle is alpha 2. So, that will be equal to sin alpha 2 divided by V p 2 as alpha 2 is 90 degree. So, we can write this is 1 by V p 2 and so our sin alpha 1 is equal to V p 1 divided by V p 2 as sin 90 degree is equal to 1. So, if I now derive the expression of T r which is refracted rays. So, this will be suppose this thickness is Z 1. So, this will be the Z 1 divided by V p 1 cos alpha c, because now this as alpha 2 is 90 degree. So, your alpha now alpha 1 is equal to alpha critical. So, and how we are getting that? So, it is this path, this value is Z 1 and this angle is alpha c, this is alpha c. So, we can determine this will be the Z 1 divided by alpha cos alpha c. So, if I divided V p 1, so this will give that time required to travel this distance S 2, say this is A and this is P. So, this is basically the travel time of S A, then plus the travel time of your A B, then plus travel time of B G. So, B G will be the same as Z 1 divided by V p 1 cos alpha c, and the A B will be plus A B will be x n, this is the x n minus this distance and this distance. So, this distance I can because this is known, because the Z 1 I know this is Z 1, this is alpha c. So, I can determine this distance. So, this distance minus 2 Z 1 tan alpha c divided by, as this is traveling with V p 2. So, this will be V p 2. So, this is the expression. So, some as I know that sin I c is V p 1 V p 2. So, similarly, cos I c will be 1 minus B p 1 by V p 2 whole square. So, this will be equal to root over V p 2 square minus, this is square, minus V p 1 square divided by V p 2. Similarly, I can write tan I c will be equal to V p 1 divided by root over V p 2 square minus V p 1 square. So, sorry, this is not I c, this is alpha c, all are alpha c, because we are using alpha here. So, this is alpha c. So, now we put this tan alpha c value here, we put cos alpha c value here. Now, if I put these value and then simplify this equation. So, if I put, so this is our equation number 1, and now if in this TR equation, if I put all this tan alpha c, cos alpha c in this equation and simplify it. So, I will get the final expression of TR will be equal to x n divided by V p 2 plus 2 z 1 root over 1 minus V p 1 square minus 1 by V p 2 square. So, this is our equation number 2. So, our equation number 1 was that this is the direct rays equation. So, that is T d equal to x n by V p 1. So, this is the equation number 1. So, we have this is the refracted rays equation travel time, this is the direct rays travel time, and we are measuring the first travel time. So, instead of again taking one particular geophone, here also we will take n number of geophone and then we will draw the graph. So, here, so we will draw the graph. So, this is our x n and this is the t. Remember that this t is the first arrival time of the wave. So, now, so as I mentioned, if we increase the distance from the geophone to the source, then the possibility of the refracted wave will reach first. So, at when the distance is very less, then the direct ray will reach first to the geophone. If distance increases, the refracted ray will reach first to the geophone. So, and we are measuring the first arrival time. So, what we will get for, suppose this is the first position of the first, second, third, fourth and so on n number of geophone. So, we will get this type of point. So, if I join these points, so we will get this type of curve. So, which indicates that this path will follow equation number 1 and this curve will follow equation number 2. And if I extend this line, so this will give the critical distance x c, where both the curves or both the rays is reached at the same time. So, we can say the slope of this curve, will give V p 1. This is the slope of this curve, equation number V p 1, and slope of this curve will give V p 2. So, this is V p 2, sorry 1 by V p 2, this is 1 by V p 1. So, this is slope of this curve will give 1 by V p 2, slope of this curve will give 1 by V p 1. Now, if I extend this curve, so this will give T 0. Now, as we are extending the equation number 2, so this is T 0 corresponding to x n equal to 0. So, if I put this value in equation number 2 from equation number 2, so this is T 0 will equal to, this is 0 to z 1 root over 1 by V p 1 square minus 1 by V p 2 square. So, 1 by V p 1 I will get from slope of this curve, 1 by V p 2 I will get from slope of this curve, and T 0 I will get from the curve, this is the T 0 value, and then only unknown is the z 1. So, I will get the z 1 value. So, now this is the one way we can calculate the z 1. Another way that we get the x c. Now, x c is the point where both the rays will reach first. So, we have to equate the equation number 1 will be equal to equation number 2. So, we equate these two equation, instead of x c x n we put x c. So, x c will get from the curve, V p 1, V p 2 will get from the slopes, and only unknown is the z 2. So, this is the critical distance approach, and the first one is the t 0 is the time intercept approach. So, any two approach you can choose to determine z 1. So, but again there is a condition that your velocity of the wave should be increases with depth. Now, I will solve one example, then you will see that if I take so, this is the curve. We can see not only one layer, we can calculate the with this change of slope, we can determine the velocity of. So, this will give us the 1 by V p 1, this will give 1 by V p 2, and this is give 1 by V p 3, and so on. Similarly, we can determine the thickness of the z 1, z 2 like that. Now, so if I solve one particular problem, so this is the example problem where we have done some refraction survey at a site, and you are getting the, we have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 geophone, and the distance of the geophone from the source is this one 2.5, 5, 7.5, 10 to 50 meter. And the time of the first arrival of the wave, which is in millisecond, remember that this is in millisecond. So, these are the values. So, these are the values and these are the distance. So, what we have done? We have drawn it in a x n versus the first arrival time of the wave. So, this is the curve. So, we have drawn this curve. So, this is the x n and this is the time, which is millisecond into 10 to the power minus 3 in second. So, it is in second 10 to the power minus 3, because these values are in millisecond. So, now if I look at this curve, that there is a different slope, you can see that. So, what are these slope? We can identify this slope. So, this is one slope. The next one is this one, and the third one is this one. So, from this curve, from this test data, we can determine this slope will give 1 by V p 1, this slope will give 1 by V p 2, and this slope will give 1 by V p 3. So, now we have done the calculation, and from the slope what we are getting? We are getting that V p 1 is equal to 500 meter per second, V p 2 is equal to 1429 meter per second, and V p 3 is equal to 3663 meter per second. So, we are you may get some different, slightly different values, because that depends on how you are drawing this curve, because we are joining this curve. But this is the three slopes, there is no there is no doubt, but you may get slightly different values what I have received, but that should be close to these values. Now, this is we will get the velocity of the each layer. Now, thickness I will get if I extend this line. So, here if I extend this line, it is 10, and if I extend this line, so what I am getting, this is another 20. So, here the t 0 value, here 20 into 10 to the power minus 3 second, here 10 into 10 to the power minus 3 second, this is the t 0. So, now from here we will get the value that our z 1 is equal to t 0. If I write in a simplified form of this equation, V p 2 into V p 1 divided by 2 root over V p 2 square minus V p 1 square. Now, if I put these values, you will get z 1 is 2.7. So, t 0 is 10 into 10 to the power minus 3. So, if I put t 0 is equal to 10 into 10 to the power minus 3 and V p is these values, is this value what we have received. So, we will get z 1 is 2.7 meter. Similarly, we can get z 2 also, the expression of that T r in terms of z 2 I am just given, which is x n V p 3 plus 2 z 1 root over V p 3 square minus V p 1 square divided by V p 3 square V p 1 square plus 2 z 2 then into root over 1 by V p 2 square minus 1 by V p 3 square. So, this is also 1 by V p 1 square minus 1 by V p 3 square. So, similar values here. So, here also if I extend these curves, so here this is the t 0 we are getting. So, t r will be the t 0 and this t 0 we are getting here 20 into 10 to the power minus 3 second, and we put this value x n is equal to 0 and we z 1 will get from here and V p 1, V p 2, V p 3 will put from here. So, only unknown is z 2 and z 2 value is coming out to be 7.21 meter. So, this derivation I have not done. So, this is for 3 layer system. So, here we can do for the n number of layer system also. So, I have done the derivation for 2 layer system, but you can extend it for 3 layer system, you will get this type of expression of T r. So, here these are the 3 velocity of the wave and these are the thickness of the each layer 2.7 meter and 7.21 meter. So, these are the example. Now, the next thing is that if you are not good result because of your condition is not satisfying, that your velocity is not increasing with depth and there is a hidden layer where it is giving the opposite trend, then you have to go for the seismic cross hole survey, which is simple, that you construct 2 or more boreholes, then this is your source and you put the receiver here, you know the distance, measure the time, simple you will get V s or V p, just distance divided by time, which is simple. Here you can collect the soil sample also, because you have the boreholes. So, here whether it is a increasing or decreasing, it does not matter, but the problem here it is time consuming, you have to construct boreholes, but the other method seismic refraction test, where you do not need to go for any borehole. So, which is very I mean time saving, in a very less time you can get the properties, but here we have to go for the borehole, which is time consuming. But if the soil layer is not satisfying the condition of seismic refraction test, then you have to go for the seismic cross hole survey. And then but among these 3 tests, if your soil layer is satisfying the condition, seismic refraction survey is most acceptable and we use that. Now, once we get the velocity, then what we will do? We will then, so this is the if we have different this is for the one receiver, this is for the multiple receiver, as to minimize the error. And now, once you get the velocity, either the V p or V s, so these are the expressions. So, you will get the soil properties. So, this is the G is the shear layer, rho is the density of the soil. So, remember that density means rho is equal to unit weight divided by the G. So, this is, so if I know the rho or the unit weight and G is the G, we can take 10 or 10 meter per this second square. So, that we can use for the G, and this is the velocity V s that you are getting. So, if you know the velocity, if you know the density, then we can determine what is the shear modulus of the soil. Similarly, K is the bulk modulus of the soil. If I know the V p, if I know the G, if I know the rho G get from these expression, then we can calculate the bulk modulus of the soil. So, these are the modulus that you are getting from this velocity. So, that means ultimately from the velocity you are getting the soil properties as well as the thickness of the soil layer. But one last things I want to mention before I finish this lecture, today's lecture, that from here, as I mentioned that your velocity. So, if I take the Vs is equal to G by rho. So, I mentioned that as the density increases, velocity increases. But here your density from this expression, if I say G is constant, then density increases means velocity will decrease. So, it is not satisfying, actually it is not true, because when your density increases, your G is not constant, G is also increases. So, G is also increased. So, that is why overall the velocity of the soil increases. So, if your density increases, shear modulus is also increased and the velocity of the wave is also increased. So, this with this note I am finishing this today's lecture. So, this is the last lecture of soil exploration. So, next class I will discuss about the shallow foundation, and then there I will discuss how these properties will use to design our foundation. Thank you.